Hello students, Deepak Pandey here, and this is the fourth episode of Breaking It 2020 in 45 days. In this episode, I'm going to discuss those problems where we have chemical reactions. If you have covered the previous episodes, you know that in all those episodes I have discussed only those cases where there was no chemical reaction. So what makes the problem different when there is a chemical reaction? Let me take a simple example of nitrogen reacting with 3 molecules of hydrogen to produce 2 molecules of ammonia. This is a very simple, very well-known and common chemical reaction. Now, if you see the molar mass of nitrogen, it is 28 gram per mole. The molar mass of hydrogen is 2 gram per mole because there are 3 molecules, so multiplied by 3. So, according to the stoichiometry, if 28 gram of nitrogen reacts, then 6 gram of hydrogen should react. So, what is the total amount which is reacting? 34 gram. The mass of ammonia is 17 and 17 multiplied by 2 is 34. So what is the mass of ammonia produced? 34 gram. So when a reaction is taking place, 34 gram of reactants are getting consumed. They will vanish from the system. And simultaneously 34 gram mass will appear of ammonia. Fine. So what happens to the total mass? What do you think? So during a chemical reaction, at steady state, the total mass remains unchanged. You cannot create a new total mass. You cannot destroy a total mass from the system. Total mass during a reaction, whether there is a reaction, whether there is no chemical reaction, the cases of no reaction we have already discussed, and we wrote that in is equal to out, whether it is for total mass or it is for species mass. Here also you are observing that the total mass initially and the total mass finally is going to remain same. Fine. But what makes the things here different? The thing which is different here is the mass of the species. If you consider those problems where there was no chemical reaction, what can you say about the mass of the species? Suppose I'm talking about crystallization operation. So in crystallization, suppose you are producing sodium carbonate crystal. So whatever sodium carbonate is entering the crystallizer, the same amount of sodium carbonate will be received at the other end. Means some of the carbonate will be present in the crystal, some of the sodium carbonate is going to be present in the mother liquor. Fine. Suppose from this side you are having 100 gram of the mixture, out of which 40 gram is the sodium carbonate. So that side, the product side, one stream will be for the crystals, one stream will be for the mother liquor. So total mass is 100 gram and total mass after the process is also 100 gram. In this 100 gram, 40 gram mass is of sodium carbonate. Out of that 40 gram, suppose 10 gram is present in the crystal. So rest of the 30 gram is going to be present in the mother liquor. So when there was no chemical reaction, either you talk about the total mass or you talk about the species mass, they do not change. That is the thing which is different here. When there is a chemical reaction, when I'm talking about total mass, definitely it is going to remain same. But when you talk about species mass, the species nitrogen mass is going to decrease because it's a reactant. Hydrogen mass is going to decrease because it's a reactant. And ammonia mass is going to increase because it's a product. So when there is a chemical reaction, the species mass has to change. And the only case when species mass can change is when there is a chemical reaction. What about total mass? They are never going to change. So that is the thing which is different here. Fine. Now I'm giving you a table which will make you the concept more clear, that what is the thing which is going to be different when you write balances on those systems where there is no chemical reaction. This is the table I have made for the better understanding of the picture when there is a chemical reaction, right? So we have learned in the previous episodes that the mass balance equation, the final mass balance equation was in is equal to out in all the previous problems in the previous sections that we have discussed here. Okay. Now this equation in is equal to out is definitely valid at steady state only. If there is accumulation, then there must be a third term which should be included here. We are not discussing right now those cases when there is accumulation. If there is accumulation, that part is called unsteady state balance. Okay. So in is equal to out was valid in all the previous problems that we have discussed. Let us check that if this in is equal to out is valid in which cases and in which cases this equation in is equal to out is not valid. Definitely all the cases we are discussing here are from steady state. Fine. So I have made a column here that suppose when you are writing balance for total mass and when there is no chemical reaction, can you write n is equal to out? When you are writing balance for total mass and when there is a chemical reaction, can you write n is equal to out? So like this, you have to complete this table. You can pause this video for 1 minute and try to complete this table. I hope you have completed the tables. Now, for the total mass, when there was no chemical reaction, we have already done this section. Definitely, you'll say that yes, this equation is valid here. Now, when there is a chemical reaction and you want to write total mass balance at steady state, I have just explained during the with the help of that example N2H2 2NH3 that yes, this is also valid. Fine. Now, when I'm talking about species mass, what is the meaning of species? The components, right? Suppose in this case nitrogen, hydrogen, ammonia were the species. In case of crystallization, suppose water, sodium carbonate was the species. Fine. So when there is no chemical reaction, when you write the balance of species mass, the equation becomes n is equal to out. So yes, this is valid. This table is going to help you a lot in clearing the concepts of the mass balance equations when there is a chemical reaction and when there is no chemical reaction. When there is a chemical reaction, can you write this species mass n is equal to species mass out? Definitely not, because if there is a chemical reaction, as I told you, that definitely the species mass is going to change. If it is reactant, going to decrease. If it is product, going to increase. So I cannot write. No. So what can you write here? If it is a reactant, suppose, then you will write n minus out minus reacted is equal to 0. If it is a product, then you are going to write n minus out plus generated is equal to 0. Why 0? Because steady state. Total moles without chemical reaction, total mass is also same, total moles is also same. Nothing is changing here. Okay, only the species is going from one stream to another stream. The total mass remains same, species mass remains same, species moles remain same when there is no chemical reaction. So definitely yes and yes. When the mass of a species or the moles of a species can change, only when there is a chemical reaction. So with chemical reaction, when you write the balance for total moles, can you write n is equal to out? Definitely not. And this one is very important, because here most of the students are making mistakes. I'll explain this point in detail after a while. Species moles, no. Inert mass, now if there is a chemical reaction even present and you are talking about inert, it is not going to take part in the reaction. So definitely its inert mass is going to be same whether there is a chemical reaction or not, and even inert moles are going to be same whether there is a chemical reaction or not. Okay, so go through this table once, that when you are writing balance for the total moles, you cannot write total moles in is equal to total moles out if there is a chemical reaction. And I am again making this 3-star point because this point is very important. Frequently I am going to use this point, right? Now of course there are some exceptions, so I am going to discuss this point first in detail. Okay. Suppose there is a reactor, any reaction is taking place. I'm not writing the stoichiometry here. This is F kg fresh feed, this is P1 kg product, and this is P2 kg of some other product. Fine. Suppose I'm talking about steady state. Okay, can you write F is equal to P1 plus P2? Think about it. This statement is always true at steady state obviously, or there are some special cases only when this statement is true. Think about it for a minute and try to answer yourself whether this statement is always true or not. There is a chemical reaction, please remember, and I'm talking about steady state. If you have understood my discussion, the previous discussion, you'll understand that this is always true, because what is this? The total mass entering. What is this? The total mass leaving. So whether there is a chemical reaction or there is no chemical reaction, it has to be same, right? Now let us consider a second scenario. There's a reactor. F moles are entering, P1 moles are leaving, and P2 moles are leaving from here. Some reaction is taking place. Can you write F is equal to P1 plus P2? Again, think about it, whether it is always true or only in some special cases. Okay, so now this case is not always true, and I'll say that generally, of course there are some exceptions. I'll give you that exception as well. I'll tell you about that exception as well. So F is generally not equal to P1 plus P2, and this is the concept that you have to understand while you write the total mole balance on a chemical reaction. Now you may ask, sir, if this is not always true, why can't we use this during a chemical reaction? Now, as you know, you have studied in your high school that if you talk about a chemical reaction, the stoichiometric coefficient of a reaction, suppose 1 mole of nitrogen reacts with 3 moles of hydrogen to give 2 moles of ammonia. So this 1, 3 and 2, these are called stoichiometric coefficient. What they represent? You know that you have learned this in your basic school level education, that these stoichiometric coefficient represent moles and they do not represent mass. You cannot say that 1 kg nitrogen react with 3 kg hydrogen to give 2 kg ammonia. You should say that 1 mole of nitrogen reacts with 3 moles of hydrogen to give 2 moles of ammonia. Fine. So when there is a chemical reaction, we work in terms of moles, not in terms of mass, and we are always comfortable solving the problem in terms of moles and not in terms of mass. Even if you solve the problem in terms of mass, at some particular step you have to convert it into moles. So that is why when there is a chemical reaction problem in process calculation, you always take the values in terms of moles and not in terms of mass. So this thing will not be used during a chemical reaction, so you can never write this. You should always solve the problem in terms of moles, and whenever there is moles, you should never say that F or total mole in is equal to total moles out. In some cases, you can write this. What are those cases? Suppose there is a reaction which gives A giving C. What is so special about this reaction? 1 mole here and 1 mole here. So if the stoichiometric coefficient on the left hand side, on the reactant side, is equal to the stoichiometric coefficient on the product side, and you are having F moles of the feed which are reacting, whatever be the conversion, doesn't matter, P2 moles and P1 moles. Now, can you write F is equal to P1 plus P2? Definitely yes. So this is the special case when total moles in is equal to total moles out. But if the stoichiometric coefficients are not like this, then for example, if, for the production of ammonia, the right hand side stoichiometric coefficient is 2. On the left hand side, the stoichiometric coefficient is nitrogen plus 3 hydrogen, which makes it 4. So 4 is not equal to 2, and therefore you cannot write total moles in is equal to total moles out. So first, this idea must be clear before you attempt any problem on chemical reaction. Okay, I'm repeating what I have, I'm trying to make clear by this discussion. During a chemical reaction, we will never solve the problem by using total mass or component mass. We will always write the balance of moles. And when it is about moles, the total moles do not remain same during a chemical reaction unless you are dealing with a particular special kind of problem. So whenever you are writing total mole, never write total mole in is equal to total moles out. Fine. So I hope this discussion makes it clear that what is the difference between reaction problems and the problems with no chemical reaction. Now let me explain the concept of limiting reactant and excess reactant, and then it is very important topic for GATE, that how to calculate the percent excess of a reactant used in a chemical reaction. Most of the questions in process calculation, if the examiner wants to frame confusing kind of problems, then most probably it will be from the problems which contains chemical reaction, and most probably they are going to ask you the percent excess. Fine. Suppose I'm considering a reaction here. Okay, I'm not going to explain here everything theoretically. It is going to take a lot of time. We are here to save time. Okay, I'll take the example of a question and then I'll explain what is percent excess, how to calculate percent excess, what is limiting reactant, what is excess reactant, and all these concepts. Suppose you have a reaction that is combustion of methane. I hope all of you are able to write this reaction. In GATE examination, if it is a combustion of a hydrocarbon, it is possible that the reaction will not be provided to you. So you must learn how to write the combustion of a hydrocarbon and how to write the balanced equation. If there is any other reaction, no need to remember any reaction, it should be definitely provided in the examination. But yes, you can remember how to write and balance the combustion reaction. Now suppose this is a reaction taking place. Now if I ask you which one is the limiting reactant here, if you're saying that oxygen is the limiting reactant or methane is the limiting reactant, then I should say you're wrong, and you can't find the limiting reactant till I give the complete information here. Now suppose at time t equal to 0, when the reaction started, right, you have 100 mole of methane, fine, and you can say a very large supply of air. Okay, suppose how many, what is the supply of air? Suppose you are having 5000 mole of air, fine. Which one is the limiting reactant? In process calculation problems, when the examiner says air, it means air only. Do not think that examiner is writing air and he wants to say oxygen. No, oxygen is written as oxygen and air means air. So if I'm writing here air, it's not oxygen, it's air. You must know how to calculate the number of moles of oxygen from the moles of air. So if it is 100 mole methane and then 5000 mole air, so what is the number of mole of oxygen here? 0.21, 21% oxygen. By default, you can assume that the atmosphere contains 79% nitrogen and 21% oxygen if it is not provided in the problem. So 0.21 multiplied by 5000. Okay, that is the amount of air. Now that is the amount of oxygen, I'm sorry. So in this case, the amount of oxygen is known to you, the amount of methane is known to you. Now you can check which one is the limiting reactant and you will come to know that limiting reactant is methane. How to check? Divide this by stoichiometric coefficient. Don't divide 5000, okay, because it is air. Divide this by the stoichiometric coefficient. The case where you are going to get lesser value will be the limiting reactant. Okay, so what is 5000 into 0.21? I guess it is 50 into 1, that is okay, 1050. I guess you can check the calculation, but definitely it is going to be higher. Okay, so this value divided by 2 and this value divided by 1, the value which is less is the limiting reactant. The reactant for which the value is less, and you are going to find that the methane is the limiting reactant. I hope you know already how to calculate the limiting reactant. Now, if this is the limiting reactant, the second one should be called as excess reactant. Fine. Now, once you find the excess reactant and once you find the limiting reactant, there comes the concept of percent excess reactant. Very, very important topic. So, percent excess reactant. First of all, for which reactant you find the percent excess? The reactant which is present in excess, for that reactant we have to find percent excess. Okay, so percent excess for which reactant I am going to find here? Percent excess of oxygen, right? Okay, so percent excess of oxygen will be equal to, I am giving you the formula in terms of oxygen only. I am not writing the general formula, I am not writing the derivations at all. So percent excess oxygen is equal to how much oxygen you are feeding, right, minus how much oxygen is required theoretically. I'll come to this point. What is theoretical requirement of oxygen? Divided by O2 theoretical multiplied by 100. Fine. Right. So what is O2 fed? We already know. Now what is this O2 theoretical? So for calculating O2 theoretical, very, very important concept. You should remember 2 points, right? Theoretical O2. Not only O2, any other reactant which is present in excess. Two things are required. First point, It is the O2 required to first react completely with the limiting reactant. Fine. Means O2 theoretical is the amount of oxygen, moles of oxygen required for the 100% conversion of limiting reactant. 100% conversion of limiting reactant. Okay. Second point. Assuming there is no side reaction. There is no side reaction. These 2 points are important to calculate O2 theoretical. I'm going to explain these two with the help of some examples. Right? Once you know O2 theoretical, O2 fed is already given to you. What you can calculate? Percent excess O2. Now, in this case, how much oxygen, how many moles of oxygen is required to react completely with the methane? Now you may ask that, sir, what is the conversion here? Now I should tell you that conversion is not required for calculating O2 theoretical. What is the meaning of theoretical? It is something which is fictitious, right? This is not happening in reality. Theoretical O2 is the oxygen required for 100% conversion of the limiting reactant, assuming there is no side reaction. In this reaction, there is already no side reaction. Even if there is a side reaction, we are going to assume that there is no side reaction and then calculate the oxygen required for 100% conversion of the limiting reactant. Fine. So, when we are talking about O2 theoretical, there is no meaning of discussing about the actual conversion of limiting reactant. Whatever be the actual conversion, it may be 30%, maybe 40%, it may be 100% also in reality. But for calculating theoretical O2, we are talking about the case that if 100% conversion occurs, then what is the O2 required? So what do you think? For 100% conversion of methane, how many moles of methane are there? 100 mole. According to the stoichiometry, how many moles of oxygen is required for 100% conversion? I hope you can easily calculate that 200 moles of oxygen will be required. So O2 theoretical becomes 200. I am taking other examples as well. So in this case, O2 theoretical is equal to 200 mole without worrying about the actual conversion. Let me take another example. Suppose I am saying CH4 reacts with 2O2, giving you CO2 plus 2H2O. And initially I had limiting reactant is equal to 100 mole. Now in combustion operation, most of the times the hydrocarbon is the limiting reactant. Okay. And suppose conversion of CH4 is given as 50%. Now in this case, what is O2 theoretical? Many students, what they answer? That, sir, out of 100 mole, only 50 mole will be reacting. So 50 into 2 is equal to 100 and 100 should be O2 theoretical. Now let me explain the difference here. That 100 mole is the O2 which is actually reacting, and this which I am writing here has nothing to do with the reality, right? I told you that it is something which is fictitious. We have assumed, we have introduced a definition like this. O2 theoretical, we have defined that when 100% methane reacted, what is the O2 required for that? So what is O2 theoretical here? Again 200 mole. Let me take one more example. CH4 plus 2O2 giving you CO2 plus 2H2O, and suppose side reaction is also taking place, CH4 plus 3 by 2O2 giving CO plus 2H2O. I hope the reaction is balanced here. You can check. Fine. Suppose initially we had 100 mole of methane and 80% of this methane is reacting. So if 80% methane is reacting, how many moles of CH4 is reacting? We'll say that, okay sir, 80 mole reacts. Where is the rest 20 moles? It will be there in the products. Fine. Out of this 80 mole, suppose 60 mole reacts by this reaction and 20 mole reacts by this reaction. This is the actual scenario. I was having 100 mole of reactant. Out of that only 80 mole is reacting because the conversion is 80%. Out of the 80 mole reacted, 60 was reacting by this reaction, 20 was reacting by the side reaction. In case of combustion, the reaction which produces carbon monoxide is considered as the partial combustion reaction, and that is considered as the side reaction. Now in this problem, what is O2 theoretical? If you have understood the definition, you can easily answer, otherwise you may get confused. So please think for a while, and you can always calculate before me that what is the value of O2 theoretical. In this problem, O2 theoretical is also equal to again 200 mole. It is not equal to 60 into 120. It is not equal to 80 into 160. It is always equal to 100 into 2. This one is quite important concept, that for calculating O2 theoretical, forget this reaction is taking place. Forget this reaction. Also forget that the conversion is only 80%. Then if you forget these two things, then what is the amount of oxygen required to completely react with CH4? 200 mole. Now what is O2 fed? That must be given in the problem. Suppose if O2 fed is 100, then 100 minus O2 theoretical divided by O2 theoretical. Fine. Sorry, O2 fed is not 100. I'm sorry. O2 fed can be calculated from here. So O2 fed minus 200 divided by 200 into 100 gives you the percent excess oxygen. Now there are some important points. The first important point is percent excess oxygen and the value of percent excess air, they are always same. Because air and oxygen are always found in a proportion. So suppose the question says find percent excess air and you are calculating percent excess oxygen, the value is going to remain same. Second thing, percent excess is independent of actual conversion. Percent excess is independent of actual conversion. Why this? What is the formula for calculating percent excess? Oxygen fed minus oxygen theoretical. Now as I have explained, whatever was the case, what was oxygen theoretical? 200. If oxygen theoretical is independent of actual conversion, the value of percent excess is also independent of actual conversion, right? Next point. If percent excess is given in any problem, suppose if percent excess is given, fine. What is its use? If percent excess is provided in a problem, the value is provided in a problem, it should only be used, only and only, no other use, to calculate O2 fed. Why I am taking O2? Because I am assuming O2 is the excess reactant. There may be other reactant as well. Or suppose if percent excess is given, you can calculate O2 fed. If O2 fed is given, you can calculate percent excess. I am giving you one shortcut method. Okay. So let me write it here. I am giving you a shortcut method. And this method is just coming from the basic formula only. Suppose percent excess is 30%. Percent excess O2 is 30%. It is given in the problem. So what is O2 fed? You can write this directly as 1.3 times O2 theoretical. This thing is coming from the formula only, you can check. If percent excess is suppose 80%, you can write this as 1.8 times O2 theoretical. If percent excess is 100%, now here most of the students are making mistake. If it is 100%, they simply write sometimes as O2 theoretical. It is twice of O2 theoretical if you follow this. And here also most of the students are making mistake most of the time at this value. If percent excess is 150%, the student multiply the O2 theoretical by 1.5. So do not do these mistakes. It should be 2.5 of O2 theoretical, right? So I hope in this video I have explained very clearly that what is the difference when there is a chemical reaction and there is no chemical reaction, and how to calculate O2 theoretical and percent access oxygen. There are various problems based on percent access in GATE previous year. You can always try to solve those problems. In the upcoming video, I am going to solve 1 or 2 problems based on chemical reaction, and then we will discuss the material balance on those systems which have recycle and purging in the presence of a chemical reaction. Thank you very much. Keep sharing and keep following the series.